Welcome to C Programming. In today's lesson, we're going to talk about a dynamic data structure called linked list. So a linked list is a dynamic data structure, meaning that each element in this data structure will be created dynamically using memory allocation, and then each element will be added to this linked list by using pointers. So how will this work? So let's look at the following slide. A linked list is basically dynamically allocated links. This is one link and this is another link. But the difference is this link and so forth is not stored in the same manner as an array that's continuous next to each other. These links are generated dynamically, and in each link there will be data, and this can be more than one or two variables in this link, and then you also have a pointer in your link, and this link will point towards a new link, and this link will have the same. It's got the data and it's got a pointer that will point towards another link, and so forth. And the last link in this data structure will point towards null, meaning the end of this linked list. So a linked list is basically a dynamic array, but it's not allocated like an array in consecutive order in the memory. It's all over the place, but the pointers in each link points towards the next link, and that will keep the order. So a linked list can grow and shrink while the program is running. So you can create links whenever you want to. You can go and delete links, and it will not hamper the other links. If you maybe delete this link, the other links will stay intact, and you don't have to recreate them. So in the case of using the calloc statement, you need to delete the whole array before you can recreate a bigger array. And with linked lists, you can just go and add links whenever you need to grow your list. So that's the linked list, that's the basics of linked lists. So let's jump into the coding and have a look at how we implement linked lists. And we need to understand how do we insert a new link, how do we delete a link, and also how do we display the full linked list. Okay, so let's jump to the coding and see. So in CodeBlocks, we will create a new empty file. And this is going to be quite a rather big program. So just hold on, try to understand it, and try to do it afterwards. Great, so we will start. Oops, before we start, we always need to save first, and we will call this linked list.c. Great, so we start off with hash include stdio.h, and we continue with our main function, int main void return 0. Great, so now we've got our basic template. We build and run just to check that everything is working. I'm just waiting still. There we go. There's our command prompt, everything compiled and built successfully, so we can continue. Great stuff. So first of all, a linked list, each link we see as an element. So in this element there will be data, but there will also be a pointer that's pointing towards the next link. So we are going to use structures to enable us to make one link or one element, or we always, or most often call it a node. We will create a node by using a structure. So in the structure there will be a data variable, or there can be more than one data variable, and there will also be a pointer variable that will point towards the next link, node, or element. So we will start by creating our structure. So we will say struct node, and now we will create an integer that will be our data, and we need to create now a pointer that will point towards the next node, and a pointer that will point towards the next node must be of type struct node then. Okay, and struct node is the pointer will point to another node, so we need to say struct node. So we've got a next pointer. So in each node there will be a next pointer that will point towards the next link or node. And that is the structure. I'm just going to type def this structure just to make it easier to create new links. So we're going to say type def struct node, and I'm just going to say node. So I will work with node throughout the program from now on. Then we need to start in our main function. Great, so let's go to our main function. In our main function, I'm just going to close this logs. In our main function, we need to go and create a pointer variable that we will call the start pointer. Now this start pointer is not a node. It's just a pointer that will point to the first node in the linked list. This is necessary because we need to know where the linked lists start. If we don't know where the linked lists start, we will not be able to add new links or delete links or display the complete linked list. We need to have a pointer variable that will keep track of the first node in the linked list. The rest, the next pointers in each struct will keep track of the next pointer and so forth. But we need to have a start pointer just to know where the linked list starts. So we will create a start pointer. We will call it a start pointer. Okay, and this start pointer will be of type node, and we will call this start pointer. Great, so I'll take out this comment, it's not necessary. Now you can derive from start pointer that will be the start pointer. And in the beginning I will say start pointer is pointing towards null because the linked list is empty, there's nothing, there's no nodes in the beginning. If we have our start pointer, now we need to add nodes and so forth. So we cannot delete a node now because the linked list is empty. So now we need to go and create a function to insert new nodes into this linked list. So we will now create function prototypes. And this will be our function prototypes. So our first function will be the insert node function, or we can just call it insert. And the parameter will be first node, and it will receive the start pointer as a parameter. Now the start pointer is a pointer, but we don't want to change start pointer. So we're just going to send the address of start pointer. So we're actually sending the address of a pointer that contains an address. So we are going to do a double pointer there. And we're going to just say SPTR. Okay, so that will be the address of our start pointer. And then we want to, oops, it's not a semicolon, it's a comma. We're going to send the data or value that we want to store inside the new node. And that's all that we need to do for insert. For delete, we need to go and delete a node, we can delete that node, and we can say node is ptr, and then we will just go and delete the node. And then the last function that we need is display. And inside the display, we will just say is ptr. So for the insert function, we need to send the start pointer and we need to send a value that we want to add. For the delete, we just need to send the start pointer, and for the display also just the start pointer. And that's our function prototypes. So now we can start to program each of these functions. So I will copy and paste this function prototypes and create the open and close brackets for each of these functions. Great, so we've got 3 functions now. So first of all, we start with our insert function. So the insert function will do the following. We're going to receive the S pointer, the start pointer, as a parameter. Now we need to create a new node, because now the insert function is called to create a new node. So what do we need to do? We need to create a new node. So we're going to create a new node pointer, new node, and I'm just going to call it new node. Now in new node, we need to go and say new node must be equal to malloc. So we're using dynamic memory allocation, malloc, and we're going to tell the new node create new memory for the size of type node. So new node gets new dynamic memory of the size of node, that structure that we created. So we've got a node, new node pointer, and we created new memory for that node. Then we need to go and say new node arrow operator, and then data is equal to the value. So the value parameter that we received in the insert function, we say new node, the data will be then the value, and the new node that we insert will be the last node in the linked list. So we can say new node next pointer will be equal to null. And we always, just to make sure the spelling is the same. And data, great. So new node has now a value and it's pointing the next pointer to nothing. So that will be the end of the linked list. Next up, we need to go and create a pointer that will enable us to traverse through the linked list to add the new node at the end of the linked list. So let's assume that this linked list is not empty. So we need to create a pointer that will traverse through this linked list until we find the end. And how will we do this? So we are going to create another pointer of type node, and this will be node, and I will say this current pointer. So current pointer is going to be our pointer that will help us to traverse through this linked list. And we're going to say current pointer will be equal to dereference the address of the start pointer, and that will be then the address of the first node in the linked list. So we dereference the address of the start pointer to get the address of the first node. So current pointer will be then equal to start pointer. we do this because we do not want to change s-pointer. S-pointer must only be there to keep track of the first element or node in the linked list. So we create another pointer that will enable us to jump to the next node and the next node. So now we have created a current pointer and a new node. Before we can continue, we need to check if malloc actually worked, if the program was able to create the dynamic memory. So we're going to say if the new node is unequal to null, we can continue. And then we're going to say for the else part, the program run into a problem. So we can just use a printf statement and we can say unable to add node. Okay, so if new node is unequal to null, we know that the malloc statement worked. Now we can continue. Now we can ask again if the current pointer is equal to null. Now if the current pointer, and it's the start pointer, if the current pointer is null, we know that the linked list is empty, so we can just go and add the new node into the first position. So we can add the new node into the first position just by doing the following. We can say star dereference s pointer, and we can say new node. So s pointer is now pointing towards the new node that we created. But if the linked list is not empty, we can say else. We need to open and close curly brackets. We can say, okay, the linked list is not empty. Now we need to traverse to get to the end of the linked list. And we will use a while statement to loop or traverse through the linked list to get to the end of this linked list. So we will say current pointer, the next pointer of current pointer is unequal to null. So while the current pointer's next pointer is unequal to null, we need to traverse. So how do we traverse? We say current pointer is then equal to current pointer's next pointer. And that's how we traverse. And for this specific reason, we do not want to use s-pointer, because now we're changing current pointer, and current pointer is traversing through the linked list. Remember, this linked list is dynamic and it's all over the memory, in the memory space. So it's not next to each other. So we can't use a for loop with a counter that will count from 1 or 0 to 1 or 0 to 10 or 0 to 50. We don't know where each element or node is stored in the memory, so we need to traverse with a pointer, and that's how we do this. And then when we get to the end, the null, what we can do is we can just say current ptr arrow operator next pointer is equal to the new node. And there we have it. So this is for us to traverse through the linked list to get to the end, and then we add the new node to the end. And that's it. That's the insert function. Now let's continue. So we have created now a new node. Now we need to go and delete a node. And how do we do this? For the delete function, we need to do the same as in the insert function. We need to create a node pointer, and we're going to call it current pointer, and current pointer will point towards the same as the start pointer. Start pointer. So we've got our current pointer, and current pointer is pointing towards the same as the current pointer. And we create another one that we will call node previous pointer. Now previous pointer will be the address of the link or the node before current pointer. So we're going to keep track of two spaces, the current position and the position just before the current position. So we're going to have two pointers walking through the linked list. So what we will do first in our delete function, we will first check if current pointer is equal to null. So if current pointer is equal to null, we can assume that the linked list is empty. So we can just write to the user, oops, I pressed the wrong button again. We can say current pointer is equal to null. We can say the list is empty. Okay, so the list is already empty. If the current pointer is not null, we can also just check for one node. We can say else if current PTR, the next pointer, is equal to null. That's for the first node. If there's only one node, we can say s PTR is equal to null. Okay, so we are telling then the star pointer to point to null, and we're going to free the current pointer, that memory allocated to that node. So we just need to put this in brackets. So the first part is we check if the list is actually empty. If it's not empty, we check if there's only one node in the linked list, and then we delete that node. But then if there's more than one node, we need to then continue and check and traverse through the list to find the last node in the linked list and delete that one. So previous pointer will become equal to current pointer. And then we will start to traverse. We will say while current pointer's next pointer is unequal to null, and then we will say previous pointer is equal to current pointer. Let's just make sure no spelling mistakes so far. Current pointer, and we will say current pointer is equal to current pointer next pointer. Okay, great. So we're traversing now previous pointer and current pointer to the end of the linked list so that we can delete the last link in the linked list. And then if the traversal was done, what we can do is we can say previous pointers next pointer is equal to null. So we disabling that link from the second last one to the last one. So the second last link or node is not pointing towards the last node anymore. So previous pointer is there for us to delete that link between the second last node and the last node. So previous pointer's next pointer will be null, and then we can go and free the current pointer. So as you can see here from this is why we need to have a previous pointer and a current pointer. Previous pointer helps us to delete the link between the second last and the last node, and we use current pointer to free that memory space. And that's the delete function. Now, before we can actually start to check if our coding works properly, we need to get some output. So we will do a display function, and the display function is quite easy. First of all, we need to go and create a node current pointer, and current pointer will point towards the dereference of S pointer, so the address of the first link in the node. So first of all, the first thing that we do is we first check if current pointer is equal to null. If it's equal to null, we know the linked list is empty. But else, if it's not null, we know that the linked list have values, and we can start to traverse through this linked list. And we're going to say current pointer next pointer while this is not null. So we will traverse, and then what we can do is we will say print f, and we will display the data of each of the nodes. And I'm just going to use arrow there, and I'm going to say current pointer data. We're going to display the data, and then we can say current pointer is equal to current pointer next pointer, and this will help us to traverse through each element. But now the last element of this traversal will not be displayed, so we just need to run another printf statement, or we could just copy and paste that one, and we do this. So that's for the last element after the traversal. Okay, so we've got now our print function. This is our print function. We've got our delete, and we've got our insert, and we've got our main function. So let's start to add some code to our main function. So first of all, let's go and add a node. Oops. We will say insert. We will call the insert function. We will send the address of the start pointer, and we will add 5. And we can then copy and paste this to make this linked list a little bit bigger, and we can 5, 2, and 8. And then we can go and call the display function, and we will send the address of the start pointer to the display function. I'm just going to add 2 new lines here so that we know what's going on. And then what we can do is we can go and delete, maybe delete a node, one node, and we can go and display again and see what's the difference. So let's see if my coding is perfect. Hopefully there's no spelling mistakes. So let's build and run and see what happens. So first of all, just want to get the command prompt there. We added 5, 2, and 8, and then we displayed. So we added 5, 2, and 8. We displayed 5, 2, and 8. We had the 2 new lines. We deleted the last node, and we displayed again. And as you can see, 8 was deleted. And then we displayed again the 2 new lines. So let's quickly add something here as well. Let's do a display at the beginning and see what happens if we can display anything. And if I run this, it will tell me the list is empty. Great, so that works. And then let's check if we can delete something if the list is empty. So I'm going to display, and then I'm going to delete. So the first time we can't display anything because the list is empty. We cannot delete anything because the list is empty. Then we will add 5, 2 and 8. We will display, delete and display again. So let's see. So hopefully we will see 2 empties. Yes. So first of all, we cannot display anything because the list is empty. We cannot delete anything because the list is empty. Then we add 5, 2 and 8 and we display. And then we delete one of the nodes, the last node in the linked list, and then we display 5, 2 and 8. Just 5 and 2. And that's it, ladies and gents. This was a long class, but linked lists are very helpful when you have limited memory. It's important to understand the concept of linked lists. It's sometimes a very difficult concept to understand, but if you understand linked lists, it will be very easy to implement. And especially when you're working on devices with limited memory, you do not want to create from the beginning an array of size 100. You want to be memory efficient. So if you only need 10 memory spaces, you can create a linked list to be only 10, and it can grow by 1 until you are at your needed space. So you can grow and delete while you are running your program. So the linked list is very dynamic and it's very memory efficient, and it will help us definitely in cases like when we program a microcontroller that has limited memory space. So we do not want to create very big arrays that will just take up space and do nothing for us. We can rather use that memory somewhere else. So that's linked list. I hope you've learned something. Thank you for watching, and I hope to see you soon.